Hi everyone, welcome to your fifth lecture on spatial modeling. At this point, you all should be considering your final projects. This is something that we can have some discussion about. I'll probably post some announcements about this as well. But just keep in mind that for anybody enrolled in the 30-20 section, you are expected to be in a group of 4 for your final project. Anybody that is in the 50-20 section, these are individual projects. So we can discuss this more in either the end of these slides or a separate slide altogether as well. But just something to keep in mind, we're at about the halfway point in this short summer session. So what you've learned so far and what you'll learn in these slides is something that you can very well apply going forward. So, spatial modeling in GIS. What is a model in the first place? If we're going to talk about modeling, we need to understand basics of what a model is. Essentially, a model is an attempt at a description of reality and is meant to resemble some concept. There are multiple types of models. We have spatiotemporal or dynamic models, cartographic models, and the difference between the two of these explicitly is time. So in a spatiotemporal model, per the name, there is a time component to it. The examples we have here are pollutant dispersions and forest fires. Not only do they spread over space, but they also spread over time. Whereas a cartographic model is a static model. It is in one place in time. This is something like a land suitability analysis. These are also referred to as GIS models. Here are a few classifications of models and the differences between them. So you have descriptive versus prescriptive. A descriptive model describes existing conditions. Prescriptive is meaning to predict. Deterministic versus stochastic. The differences here are that a deterministic model assumes that each variable has a unique value. A stochastic model assumes variables to follow some kind of a probability distribution. We have dynamic versus static, which we just mentioned in the last slides, whether or not time is a variable, and then deductive versus inductive. Deductive models are based on theories, and inductive models are based on empirical data. So in static cartographic models, these look at the application of spatial operations such as buffers, reclassification, and overlay, and they utilize these to solve problems. Examples of a static cartographic model is a suitability analysis, such as a classification of land according to its utility for something, such as in this case, agriculture. There are temporarily static, where values don't change within a layer in a model over time, and it may include a temporal component when its compares change, but the layers themselves are static. So what this means is that you can have two different sets of layers where they're looking at the same data, the same type of data, but one maybe is from the 1970s, one's from the 1990s. However, these two sets of data are still different layers, and therefore there's no overlap where we're seeing a transition. It's almost like it's almost like flipping between a book. They're both pages in a book and they both have different information related about the same thing, but it's not on the same page. It's not dynamic, it's not changing. Cartographic modeling, we're combining data sets and functions and operations into any type of sequence to try to answer some form of a question. The output is typically a map or an attribute table from these various inputs. So examples of these are looking at distribution of suitable habitats, viable populations, migration routes, corridor studies, water distribution systems, species invasions, site selections, harvest scheduling, pollution response, and planning. So many different options when it comes to cartographic modeling. Again, the main kind of output of these types of models is that you want to basically answer some form of a question through either the output map itself visually or through the attribute table. You can see in this example down here that we're taking 3 separate layers to start: lakes, roads, and hydric status. We're running different operations on each of these layers. Lakes and roads are getting separate buffers. Hydric status is getting a recode. Then from there, we have buffers for the lakes and the roads, and we have a recode for just selecting wetlands. We overlay our buffers, and then we combine those buffers, overlay them with our wetlands. We take our buffers and our wetlands and we recode that to make a suitability ranking. So all of this is pretty static. It's not a change over time and space, it's just a change over space or a relation between space. We also have our dynamic or spatiotemporal models, which again look at both time and space as factors or functions into the map itself. Time passes explicitly. So you will know whether it's static or dynamic because time is very explicitly mentioned or shown in these maps. They aren't as common as our cartographic models because they're a bit more complex, but they are very powerful. So an example is a simple binary model. We want to identify areas that are suitable for a new park. The criteria we have are that we want it to be near a lake, we do not want it to be too close to a road, and we do want it to include some wetland areas. So how do we take these criteria that we have and translate it into a GIS analysis? So the first thing is lakes. We want to buffer it to have our lake buffer. Roads, we do our buffer for however many kilometers, miles, meters we want to be away from a road. We have our road buffer. And then the hydric status, as we saw, we recoded it so that it's either a wetland or it is not a wetland. Then we combine those buffers because both of those together matter for us. And then we overlaid them with our wetlands. With that, we recoded it so that we could see, okay, it either matches the criteria, so it is a buffer layer of these road buffers and lake buffers, as well as intersecting with our wetlands, or it is not. The attributes needed to make a selection are now all in the same table once this recode happens, and then we can see from that attribute table what areas do actually suit these three pieces of criteria. So now only the suitable areas are shown. This again is the entire model as you saw in the very start. So you could see we kind of started zoomed out, looked at each piece, and then zoomed back to our suitability ranking and everything that it took for us to get there. It doesn't need to be terribly complex. Sometimes it's just understanding what it is that you're asking for and what the simplest way is to achieve that. So for cartographic models, they are often represented with flowcharts. Typically, it's representing the spatial data as well as the operations in whatever sequence they were performed. If you were to be taking this during the summer or the fall or spring session, you would hear a little bit more about these flowcharts from me. This is something that for your final project, I highly recommend you include a flowchart. It's not an explicit requirement, but it is something where you are much more likely to get the points for your analysis and the tools that you utilize if you explicitly put it in front of my face. Because this shows me not only did you plan out what you were doing, but you understood the process that it took you to do. It takes a lot to actually sit and plan. How am I going to achieve A, B, and C using this software? What are the starting layers that I'm going to utilize? What types of functions or tools do I need to do to recode them, reclassify them, clip or intersect or buffer or dissolve, and all the other tools you can use? How will I combine them? Do I need to run other analyses? How may I run a suitability analysis? All of this can be shown, of course, through a multi-minute presentation, but it can most simply be shown using a flowchart. So 2 points on this. Typically, a cartographic model, which is going to be that static model, is going to be represented as a flowchart at some point. And if you represent it as a flowchart in your final project, you are very likely to score higher than if you were not to. So you can see over here, and we mentioned this in lecture 4, there are a lot of intermediary files that come up once you start doing spatial analysis of any kind. You want to make sure that you're using good naming systems, and you want to be aware that they can be quite large, so clean up frequently as you can. If there are certain things that you don't need, then delete them. Once you get to the point that you have combined buffers, you can probably get rid of the lakes buffer and the road buffer separately. Once you get to the point that you have the buffers and wetlands, everything before this can probably be removed. Now, if it is something as small as this model right here, it's not going to do you. It's probably going to take you more time to go through and delete everything beforehand than it would to just leave it alone. But imagine if you had 10 times this process. At that point, it can bog your machine down quite a bit, and you may get confused if you're not using a very good naming system. So be intentional and be strategic. So, the GIS modeling challenge. Although examining existing flowcharts is useful for learning, you ultimately have to be able to generate it yourself. So, you have rasters and raw data, you have lines, points, remote sensing. Do you want to calculate, dissolve, intersect, select? You may know about these tools, but you need to know when you want to use them and when you do not. Before you choose a modeling tool to start, there's a lot of steps that you should go through. The first and most critical is, what do you want your very end output to look like and what do you want it to be? The trip doesn't have to be long, it doesn't have to be short, but it does need to be whatever it is that'll get you to that end point. So, things to ask yourself about that output. Does it need to be spatially explicit? Or does it need to be spatially aggregated? Or does it have to be both? The difference between these is spatially explicit is a resulting GIS data layer. So that means you are going to visually be looking at that data layer. An example here is dissolving polygon boundaries to simplify the land cover classes in that data layer. Spatially aggregated means the result is a number or a set of numbers. Example here is calculating total area of each habitat type in a given county. Now, this isn't to say that a spatially explicit data layer is only going to come with some visual output, right? We may need to look at that attribute table once a dissolve function is finished, or once a buffer function is finished, once there is a union that is done, or even a spatial join that is done, so that we can see the relation of one data set to another data set. However, you can really and truly think of spatially aggregated as a set of numbers that you're interested coming out of. So output product characteristics here. You have to ask yourself, do you want a map or do you want a table of numbers? And again, spatially explicit doesn't mean that it's always just the map image that you're interested in, but you can think of it as you need those visible, physical, I don't want to say boundaries necessarily, but you need the visible to make sense of the table. Whereas spatially aggregated, once you have that table, it gives you all the information that you need. So, if you do want a spatially explicit output, you need to think of what form you want it to take. Is it points? Is it lines? Is it routes or polygons? If it's spatially aggregated, what are the attributes that are needed in the table? So now we know what the end of our journey looks like, and we want to go ahead and start identifying points. Excuse me. So identifying possible inputs. We know that the end goal is over here. Now let's go all the way to the beginning of what we may want to put in. So there are layers containing needed attributes, and there are going to be layers containing the needed points or polygons. There's also going to be layers that can be used to produce the needed points or polygons. This is typically what you start with. It's pretty rare that you just find a layer online or are sent a layer of data that already has the attributes that you need or the points and polygons. It's far more frequently, it's more of a frequent occurrence that you find a few pieces in one layer and a few pieces in another, and then you go ahead and combine them in some sort of way using the GIS so you can run the analysis you'd like. Next, you want to develop a strategy. So often the best way to map out a modeling process is to actually create this flowchart as we mentioned earlier. Once you can kind of visualize the steps using that flowchart, you can go a little bit further. And this here is just a sample cartoon of looking at the percent of birds on a beach. So your starting layers are birds and their point data for number of adults. And then you have a land cover layer, which is just some polygons. It's the NHTM 9353. You run a simple intersect on these two layers, and we get the land cover type plus the number of adults on that land cover type. From there, you select beach, and you can get some statistics to see the number of beach birds, or just straight from the layer, you can select the statistics to see the total number of birds on a beach. Very simple flowchart, and you can see just how easy an analysis can be. Then you need to debug your model and execute it. A lot of times, your model will be at least somewhat complicated. You're going to have different intermediate data layers, as we mentioned. Even if you ultimately want to do something automated, it's a really good idea to step through that process manually and study each of those layers that you create as you go. If you're going to have a bug, it's going to probably be in those intermediary steps, So if you flip through each step that you do, you can catch it and save yourself a lot of trouble. And a lot of times, as we go through again and we find these bugs and we just kind of flip through the work that we've done, we'll see that maybe there's some modifications that can be done, as sometimes things just get buggy, or sometimes you notice that there's a better data set, something isn't running or intersecting the way that you want it to. So it's just a very good and necessary component of running models and creating models to actually debug as you and before you execute. And I'd like to make a comment actually back on this slide. Just because you go through once to debug and then you execute, doesn't mean that you don't need to do it again. If you find something going wrong, don't try to focus on what the end result is and what's happening just in that very final part. Retrace your steps. Again, think about, well, what is the end goal that I wanted? What is the data that I started with? Okay, what was the order of operations and the types of tools that I used? Were those appropriate? And then, once you go through all of that, come back again and debug before you execute. So moving on, we have a sample model problem, and I think I might have actually taken out, yeah, I think I took out the slides after this for this course. So I'm going to put this here for you guys. Let's see, just say it's a question of some agricultural acreage falling within 200 meters of major roads in Northampton County. So we have some input layers, which are roads and land cover. And then we also have this task of producing a map of buildings at Morven Farms at UVA that are within 1,000 feet of both a road and a trail. We have these three input layers here. So for the first one, the agricultural acreage that falls within 200 meters of major roads in Northampton, there is a cartoon coming up. I'd like for you guys to try, I know again this is asynchronous at this point, but try to actually draw out a cartoon for how you would go about answering this question. So you have a land cover layer that has agricultural class, and then you also have a road layer, including major and minor roads. Take a pause, try to work on it, and then start looking through these. See which one your model looks most like. So this is model 1. We start off with roads and land cover separate. We do a buffer on the roads, and we select the major roads buffer from that. For land cover, we run an intersection with it in the major roads buffer. We get agricultural land near major roads. We run statistics, and that's our answer. Excuse me, that is option 1. Option 2 is that straight from the roads layer, we select the major roads, and then we run a buffer around those major roads. We run an intersection again with just the raw land cover. We have agricultural land near these major roads, or near that major roads buffer, more so. We run stats, we get our answer. Model 3, we start with land cover and we select for agricultural land specifically. Then on roads, we select the major roads, we put a buffer around those major roads, we intersect the agricultural land with the major roads buffer, and we get agricultural land near major roads, statistics, and answer. Then we have Model 4. So the same initial steps with land cover to agricultural land and then roads to the roads buffer, but instead of running an intersect like we did in Model 3, we run a clip. And then agricultural land near major roads is our next layer. We run statistics with an answer. Finally, we have Model 5. So again, we are taking a selection of major roads, putting a buffer around them. In this case, we are taking land cover and we are just doing a direct union between land cover and the major roads buffer. From there, we have land near major roads. We make a selection for agricultural land that is near major roads, run statistics, and answer. So think through these, look at what it is that you drew for your cartoon for that first question, and then we will flip through kind of what works and what doesn't. And then assessing problem number 1. So, roads and land cover. Model number 1's issue is that the buffer layer, it has no longer any information about road types in its attribute table. This is because we ran the buffer before we actually made the selection. So if you have a buffer or if you have a roadway, for example, and you do a buffer around it, that buffer layer no longer has any other information in it that's relevant to us. Then we did our intersection. At this point, there's nothing really to give us information again about those major roads. We're kind of done now. To do a buffer, just to do a buffer around roads and then to select major roads doesn't make sense for us. Model number 2, we fixed this by saying, okay, we're going to make a selection for the type of roads. Then we're going to do a buffer. Now it's not all roads have a buffer around them. It's that just the major roads do. The issue here, though, is that we didn't do any sort of a selection for our land cover type. Remember that we wanted agricultural land. So this would include all types of land covers. Model 3 would work. In addition, Model 4 would work. The only difference between Model 3 and Model 4 is the intersection versus the clip. And if you remember from Lecture 4, these are pretty interchangeable. Not always, but a lot of the times you can use one or the other. So, kind of moving a little bit further in now, looking at the biggest hurdles for us GIS users, right? We are part of the equation when it comes to map making because we are the actual deciding factors in what data we're getting, where we're getting it, how we're going to put it together. The very first hurdle is actually finding the correct data itself. After that, of course, there's the learning curve of the software. I'm sure all of you by now you felt it from the very beginning of the course of maybe it's a little overwhelming. You haven't touched the software before. You may not know where certain buttons are and what certain tools you may use. But at this point, you're probably a bit more comfortable with it. It's all muscle memory. It's all just practice. Of course, the projection issues and the overlaying of data, that again is muscle memory. It's just you kind of learn it and you learn as you go. Moving data in shapefiles, saving work, and collaboration are a few other hurdles for us GIS users. When it comes to finding data, of course, you need to identify what the study area is and what the data needs are that you have. Once you do that, you have to go through and survey what is actually available to you. A lot of the times, once you go through and you look at what's actually available to you, you're going to have to adjust your expectations a little bit. There's a lot of GIS data out there in the world. For example, we know that there is GIS data from even Living Atlas that comes straight into your software. You don't even need to actually go online to utilize it. And that's great. You have a lot of land cover data, topography data. You have some data on different animal populations and such. But a lot of the time, if you're trying to look for data such as public health data, which is a really easy example to use here, you're going to have to adjust your expectations for what's going to be available to you as a user. Some things are hiding behind paywalls. Some things are hidden behind even more important stuff like firewalls when it comes to things like HIPAA data, for example. So you may have some great ideas and you may have some great goals, but the data isn't just always going to be readily available for you to utilize. Once you do find some sort of data, you need to either acquire other data, maybe you need to create additional data sets to relate to the ones that you found. You need to standardize your data in some type of way, and you probably will end up having to reformat it to suit your needs. And eventually, once you get through all of that, you then actually need to do the analysis or run the model itself. So there's something called a whirling data vortex from GIS. And this is questions that you may want to answer, the questions that you can answer, the data that you can get, and then the data that you need to answer the questions. And all of these are constantly shifting around. You may have one, you may not have another. You may have three, but you may not have the fourth. You may have one, but you don't have the three. So it's just something to keep in mind. You can have all the data in the world, but if there's one component missing for something that you need to run an analysis, then you may not be able to answer that question in the way that you wanted to. So a suitability analysis, an example here, which is setting criteria. We want to select a site for a brand new home. We have 5 general criteria. We want it to be in a floodplain. We want a slope. We want to choose based on floodplain. We want to choose based on specific slope, as well as a specific aspect, specific soil type, and a distance from the road. So we have 5 criteria here. Some of these are quantitative criteria, like whether it has a slope or not. Some are qualitative, like what type of soil is it. We work with subject matter experts on determining what the criteria should be. So we go ahead, we work with our subject matter experts, and this is the very simplified output that they give us, right? Our general criteria is on the left, our refined criteria is on the right. So we don't want that slope to be too steep, right? You don't want to just tumble out if you accidentally slip. So we want that slope to be less than 30 degrees. We want a southern aspect preferred. We want to get a lot of sunlight. We want to be able to wake up, look out that window on the southern side. So we want our aspect to be between 90 to 270 degrees. We want soils that are suitable for a septic system, so we choose soils that are on a specified list that are septic safe. And we want it to be far enough from a road for privacy, but not far enough that it's like a horror movie. So we create a boundary. We want the distance of the road to be between 300 meters and 2,000 meters, not too close and not too far. Then we have whether or not it's on a floodplain. So not on a floodplain, we want no floodplain. Our goal here is that we combine all of this information and we get a combined score or a suitability score. So you'll hear this a lot. This is a really big use of GIS is to do suitability analysis. So we can use these suitability scores to further rank the certain types of locations. We can also, in our suitability scores, say which one of these criteria might be more important to us. And we do this using weightings and rankings. So, in a simple model, your criteria will just be equally weighted. All 5 of these things are just as important to us. We're not going to add any sort of weight between them. More complex models, we may rank with criteria. So, we are going to, in this example, rank within soil layer for suitability. We'll say that the most suitable soil type is going to be sand. We'll give that a higher ranking of the number 3. We'll say the least suitable is going to be clay, so we're going to give that the lowest ranking of 1. Keep in mind that this is slightly different than in the last slides where we were kind of talking about like buffers and things. And I would suggest just going back to lecture 4 if you do get confused between the kind of rankings that we were using for some of the tools back there in spatial analysis. But keep in mind, this is a suitability criteria model, so it's slightly different. Nonetheless, we then have weighting between our layers, which is kind of the bigger thing that we see when we're running these suitability analysis. What's more important, whether you have a southern facing aspect or whether you have a septic safe soil? So you have to ask yourself, is there a trade-off? Would you accept a slightly worse aspect to get a better soil? Or would you rather have a slightly better aspect and not have as good of a soil? Then, with all this information, you also just generally have to understand that there is discrete and binary data, or there's continuous data. So discrete binary is a yes or no. Present or absent. Is it on a floodplain or is it not? We can very easily code that as 0 or 1. Continuous is often going to be a rating. It's a scale. So this allows for shades of gray. This is the slope, for example. There's ranges on that slope. There's ranges on that aspect, right? So over here, looking at discrete or continuous rankings, this here is our source layer of soil type. So just take a look at the discrete rank layer versus the continuous rank layer. If production is less than 66, then the rank value equals 0, else the rank value equals 1. So it's either 1 or it is 0. Whereas in this continuous rank layer, you can see that you can assign these based on the production. The values are scaled linearly between lowest and highest, and they're given a rank from 0 to 10. You can just see generally, this is black and white, and this has shades of gray, like our last slide mentioned. So how do you decide which one to use? You choose discrete if this is a deal killer. You either have it or you don't, and that makes a very big difference for you. You choose continuous if more of it is better, or if less of it is better. Most of the time, you do have a choice. So soil types can be designated as percolates, or doesn't percolate. You can choose that to be a discrete variable. Or you can group it into the categories based on the rate of percolation and make it more shades of gray. Most of the time, we will do both. We'll set all percolation values that are less than a certain number, in this case a liter per second to 0. We'll leave the rest as 1s, or unchanged. We want our criteria scores or our rankings to increase if things are good, but there is such thing as too much of a good thing. For example, the slope. You don't want a terribly high or a terribly low slope because it kind of defeats the purpose. So our criteria rankings may need to be calculated based on whatever that underlying characteristic is. In this case here, we want a road that is nearby, but not too nearby. So you see the suitability ranking isn't on one far end or the other, it's actually right in the middle. Same thing with elevation, slope suitability. There is too much of a slope and there is too little of a slope. So somewhere in the middle is where we're actually hitting that sweet spot. So now we have our scores for each of the criteria we need, or each of the criteria that we have, and we want to go ahead and combine them into our overall suitability score. So our major methods that we can use are additive or weighted. Additive is as it sounds. Weighted multiplies scores by different weights to signify how important one might be over the other. So over here we have criteria A layer, we have criteria B layer. Putting these together, you can see that there's a note here. B has a wider array of scores. The top score from A is only a middle grade score from B. So you see we have 1s, 2s, and 3s here, where over here our higher numbers are 5s and 7s. We add these together and we get our suitability layer value somewhere right over there. So this is an additive process. And you can see that the interpretation of the final score is pretty difficult because we don't know, are these numbers weighted equally? Is a 1 over here the same as a 1 over here? The way we solve this is by weighting our criteria. So, again, we have slope, aspect, soil type, and the distance from the road, right? We already knocked out our discrete value of floodplain or not. That's our 5th one, so we're leaving that on the side. Now we make this decision. Slope versus aspect, soil type versus distance, and is there anything that's missing? So now you see these variables over here, WA and then WB. These are our weighting values. We can choose which one is weighted as which one, and then get our suitability layer value. So these were our home site selections, right? We used our discrete rankings. We said we want the slope less than 30 degrees, our aspect between 90 to 270, specific types of septic suitable soils, and then a distance to the road between 300 meters to 2,000 meters. This here is how we actually work through it. So again, there's multiple ways for any sort of model. There's multiple ways that you can go about it. Where you may see an intersect, you maybe could have done a clip or vice versa. But to get this, we did 20 operations. 5 were raster, 19 were vector, 1 was a conversion. There were 15 data layers overall. 6 raster, 9 vector, and 2 line, 7 polygon. So you can see it's really useful to map out a flowchart and kind of think of what that end goal is, what your criteria is, before you actually go ahead and run through everything. It makes debugging much easier in the end. So break the model down into segments and examine them a bit. Over here, we have just looking at the elevation. We chose a slope, we chose an aspect, we reclassed them so it's either good or it's bad. Then we overlaid them. We have a terrain overlay layer now. We go from a raster to a vector so that we can again reclass, and we dissolve for whatever that suitable terrain is. And you can see that all visually right here. Then we look over at soils. For soils, we wanted to reclass it. It's either suitable or it's not suitable. Then we dissolve so it's black or it's white. Suitable or it's not suitable. We then go over to our roads layer. So we extracted our major roads, and then we ran a buffer for 2-kilometer buffers and 300-kilometer buffer layers. We run these over one another as our preliminary buffer layer, and we clip it. So now you can see here that these areas that are right in between are what's going to work. We have our 2-kilometer buffer layer, our 300-meter buffer layer. And boom, these are the areas that would make sense for us. Then we look at everything all over again. We have our terrain and our soils, our road buffers, we have our suitable access layer over here. We take this and reclass it to say, these are the areas that work, these are the areas that don't. We overlay terrain and soils with our suitable access layer. We overlay that with our all criteria overlay, reclass, dissolve, and we have our suitable sites. And you'll see all of this comes out as 0s or 1s. So it's really interesting looking at this in a flowchart sense versus a visual sense. all compared to the initial things that we said are make or break for us. They're yeses or they're nos. There's this range or it doesn't work. So analyzing the output tables, you can use the output attribute tables to analyze from ArcGIS. You can calculate new fields using your field calculator or attribute calculator, and you can also produce some thematic maps with color-coded scores. If you are using data in shapefiles, the attribute tables are stored in files that are ending in .dbf, and you can open them in other types of software such as R, some versions of Excel, OpenOffice Calc, I don't think any of us use that anymore, or SPSS and SAS statistical packages. So keep that in mind that your statistical analysis, or more so numerical analysis even, does not have to only happen inside GIS. So we answered this a bit earlier, but is this the only way to conduct this analysis? Most definitely not. GIS modeling is an art and not a specific science. And I would even go a step further to say it's not a math, it's a science. Because with science, you can use different methods. You can kind of come up with different methodology, different questions to ask. And that, in and of itself, is an art. So this will go for anything and everything that you're doing in ArcGIS or GIS software at all. If you can do it one way, you can probably do it another way too. And even then, you can probably do it a third type of way. Your key to success is just clearly identifying your goals and that desired output. And then from there, finding what do you have available to you to try to get yourself there. So some common errors that you'll see, and you're not really going to see them in these versions of GIS, but one of them is that when you're using older versions of ArcGIS or using shapefiles, which we do use, when you run a spatial operation on polygon layers whose attributes contain information on area and perimeter of each polygon, those area and perimeter fields do not update following a spatial operation. So you need to manually do this. You do this by just recalculating the geometry after a spatial operation. So you right-click on that area, you hit Calculate Geometry, and then you just go through the process. You choose lakes, area, whatever property you want it to be, what that area unit is, and you run it. So, spatiotemporal models, the cartographic models that we've looked at so far exploit strengths of GIS, but again, spatiotemporal models do an additional service for us where it explicitly uses time. That's not something that a cartographic model does for us. So a raster data model is most frequently used in a spatiotemporal model because rasters, as we've discussed from lecture 1, are really good at handling continuous data. They're good at handling data that has a range to it. So your deterministic model versus your stochastic model. A deterministic model is going to run once. A stochastic model is going to run multiple times. And you'll see over here, we start with a bunch of random numbers. We can get our stochastic model, or we can have our fixed input data and go in either direction. So a spatiotemporal model can be one or the other. It can be deterministic or stochastic. Deterministic is that the model output is determined entirely by the model structure and the initial conditions. Whereas stochastic, there are random elements. So a repeated run with the same initial conditions is still going to generate some range or some distribution for us. A stochastic model is going to use random numbers again to kind of generate tweaks to the model output. So instead of just one result, you get a range. And of course, as we've mentioned a few times now over the last 2 slides, it requires random numbers. So how do we introduce random numbers into GIS? For attributes, there are random number functions. And for rasters, there are tools that we have to create random grids that we can then combine with other data. So this over here is just showing you a random landscape versus a real landscape over multiple sets of years. And you can see that the different colors over here, the gray, black, and white, show you non-forest, white pine, and other forest. What's important to note here is that this is basically showing us change over time. And you can determine for yourself whether you think that this is a deterministic or a stochastic model here. If you take a gander, especially as we get into years like 250, 300 through 400, you can see a lot more of those black dots, you know? This is basically trying to show you, well, where is it non-forest? Where is it white pine? Where is it other types? And then you can see here as well in pre-year 150 fires, which is before all this section, you can see these small areas that show you where a fire had occurred. So nonetheless, issues with using GIS for models. The first and kind of most blaring one is that these models can be enormous. They can have a lot of different input layers. There may be a lot of tools that you have to use. It may take a lot of time. With that, and it ties in directly, is that they can be very complex. So sometimes what occurs in one specific raster cell has to depend on a large number of other cells. And again, it can be very wow, excuse me for that. It can be very time consuming. um, there's something called seed establishment in a cell, and this depends on, again, the number of parent cells around it. So models are very dependent on the other things going on within that model. They're dependent on the other data layers. They're dependent on the other tools that have been run and specifications that have been made. And this, again, it may be very tough on your computer. It may be very tough on your brain to figure out what tools you want to use when you want to use them. And it kind of comes back to overall, it could be inefficient depending on what it is you're trying to do and how you do it. There are a lot of capabilities of this software, but there is a cost, and sometimes a custom written model can be faster. There may be some things that you'd love to do in GIS that might make more sense to do in R or Python, and vice versa. So, in summary, you have your static versus your non-static or dynamic models, which is cartographic for static and spatiotemporal for dynamic. And you have the process of modeling down a little bit more now. You identify your end goal, then you find and modify the initial existing data. You run the analysis, you evaluate your results. And throughout all of that, you're debugging. And then finally, we've just kind of discussed some different types of models here. So this table is from your first few slides of the class, just a reminder of the different model classifications and the differences between them. Keep this in mind as you go forward with trying to kind of think about spatial modeling and how you may apply spatial modeling for things such as maybe your final projects. It is a very useful, powerful tool of GIS, and it's something that I suggest, especially with the tutorials and your assignment going forward. Just kind of keep this information in the back of your brain as you are working through them. With that, this is the end of Lecture 5. So good luck with your tutorials and assignments, and I'll see you over in Lecture 6.